A lot of work from the last year went into a new module for OpenARK, 3D object tracking. This is what I personally worked on with a team of around 6 students. We hope to incorporate this as an augmented reality module in the months and semesters to come. The problem we are focusing on is called digital twin. The goal is to track a real-life object with sufficient accuracy such that a virtual copy of that object, its digital twin, can be overlaid on top of it. This technology has different applications, from augmented reality mobile applications to industrial maintenance. Have you ever built anything out of Legos? Each Lego kit ships with pieces required for assembly, as well as a manual detailing each step with visualizations. With digital twin technology, you wouldn't need a manual at all. Instead, building instructions could be rendered onto a phone screen or a pair of augmented reality glasses directly aligned with the Lego bricks. How can we power digital twin? The solution that we focus on is called 3D object tracking. Object tracking answers the question, where is the known object in our scene? Known object refers to tracking objects that we know or have a digital model of. This is important as it allows us to develop algorithms that target specific objects. The where refers to the sixth degree of freedom, or sixth off pose of the object, its position and rotation in 3D space. This problem statement is very reminiscent of the camera tracking in SLAM. However, the difference arises from what's being tracked. While SLAM tracks the position of a camera in a scene, object tracking focuses on the position of an object in the camera frame, regardless of the surrounding environment. Some of you might be familiar with 2D object detection. It's a similar problem to 3D object tracking, finding the position of an object in an image. Modern-day deep learning techniques, driven by convolutional neural networks and more recently visual transformers, perform this task with increasing levels of accuracy. Modern-day networks are capable of outperforming humans on image classification tasks on massive datasets such as ImageNet. However, when lifting this problem to 3 dimensions, it becomes a much more difficult problem. First, what we ask of the algorithm is inherently more difficult. Instead of just classification, position, and scale, the network needs to classify position in 3D space and rotate in 3D dimensions, arbitrary objects. The loss functions need to be carefully calibrated to achieve good performance, and object symmetries need to be thought of. Second, there is much less research on point cloud processing versus image processing. PointNet 2016 marked the beginning of deep learning on point clouds in a fashion similar to convolutional neural networks. Third, the datasets are much smaller. While ImageNet contains over 1 million labeled images, the state-of-the-art datasets for 3D object tracking contain fewer than 100,000 labeled images, coming from less than 100 unique environments. Fourth, annotating data in 3D is much more difficult and expensive. This is a major contributor to the third point. Following the themes of OpenARK, we approach object tracking through the lens of augmented reality. While a majority of the literature in 3D object tracking focuses on the problem as a robotic grasping problem, our augmented reality perspective raises some new constraints. First off, we need a solution that can operate in real time at 30 frames per second at a minimum. This is because a final digital twin product would require perfect alignment of real objects and their virtual counterparts in a video or a pair of augmented reality glasses in real time. High latency would lead to misalignment due to shifting object poses. Second, we have tighter error constraints. Robotic grasping has a higher tolerance for error, as minor inference errors can still lead to a successful grasp, and this is reflected in the metrics used to measure algorithm success. Thirdly, we require both textural and geometric alignment. This refers to objects that have geometric symmetries, such as markers, but have textural asymmetries, for example, a label that uniquely identifies the object's rotation. While the robotic grasping perspective to object tracking is more tolerant to predicting the position of an object up to its geometric similarity, incorrect textural alignment is an incorrect alignment for augmented reality. The current directions of research in the object tracking field include, but are not limited to, traditional methods and deep learning methods. Traditional methods tend to rely on key point matching, 2D and 3D computer vision techniques, but Difficulties arise under harsh lighting conditions, sensor noise, and heavy object occlusion. Therefore, state-of-the-art techniques employ deep learning approaches to solve this problem. These deep learning algorithms can be divided into two groups, RGB-only methods and RGBD methods. RGB-only refers to algorithms that operate only on color images, while RGBD refers to algorithms that receive aligned color images and depth maps. The benefit of the latter is the ability to reproject the depth map into a colored point cloud using the techniques described in the 3D reconstruction portion of my presentation. A class of deep learning architectures beginning with PointNet has been developed to ingest these point clouds and infer qualities such as point-wise semantic segmentations and object poses. In our work, we focus on the third of these directions, deep learning methods utilizing both RGB and depth maps. These solutions offer the most promising results for algorithm tracking performance. Here is an example network, dense fusion, that was one of the pioneering works for RGBD object tracking. We start at the top left of the image, where our input is an aligned RGB and depth image. We pass the RGB into a CNN to get color embeddings, and the reprojected depth image, a point cloud, into PointNet to get geometry embeddings. These two are then fused in a dense fashion, hence the name dense fusion, and a global feature is extracted. Finally, pose predictions are regressed using each pixel-wise feature containing a color embedding, geometry embedding, and global feature. In this manner, the complementary sources of data work together to create more accurate inferences. A general pipeline for 3D object tracking follows the procedure above. First, we process the RGB and depth data, either separately using their own backbone networks or in a more combined manner. Next, we perform pixel-wise semantic segmentation. Then, we take a region corresponding to an object in the image frame and predict the object pose, given the pixels and points within that cropped area. Different algorithms differ on whether the tasks of pixel-wise semantic segmentation and object poses are implemented as multitask learning in one network or in entirely separate networks. We will now dive into these different stages. First, many of you are probably familiar with techniques to process image data, specifically convolutional layers. Convolutional layers are kernels that convolve through an image and process data in patches throughout the image, taking advantage of the spatial locality of pixels. Depth maps pose a different problem. Neighboring pixels don't necessarily correspond to neighboring points, as silhouettes may divide large distances in 3D space. For this reason, most algorithms rely on point cloud processing networks that operate on the reprojected point cloud instead of the projected depth map for better performance. Inspired by 2D convolutional neural networks, what we are looking for is a network that can process 3D point clouds like their 2D image counterparts. The first property that a 3D point cloud network needs to satisfy is permutation invariance. 3D point clouds are an unordered data type, unlike images, which are ordered very naturally by the rows and columns of the pixels. We can think of a point cloud as a list of points and their features in any arbitrary order. A 3D point cloud processing network should be able to process a point cloud regardless of the order of the points given. Secondly, a 3D point cloud network needs to be robust to point noise and holes. Noise arises from sensor measurement, and holes are ubiquitous. Due to the nature of the point cloud coming from a single depth sensor reprojected, there is oftentimes no back or sides to an object, only the face directly facing the camera. Using features such as point positions, colors, and normals, the network needs to be able to perform tasks such as classification, object pose regression, and point segmentation. The two major categories of point cloud processing networks are point-based and voxel-based. Here is an example of a reprojected depth map. Notice the holes on the backsides of the objects. Also, notice the holes in areas with bad depth data. The first of the two major categories of point cloud processing networks are voxel-based techniques. Drawing directly from 2D convolutional layers, these techniques involve binning 3D space into voxels or cubes, reminiscent of the TSDF from 3D reconstruction. And after populating these voxels with the points from the point cloud, the entire voxel space can be convolved using 3D kernels in a fashion similar to 2D kernels convolving over 2D images. The downside of these techniques is their inefficiency when faced with sparse point clouds, so many of the voxels are empty. So point-based techniques have risen in popularity in comparison. Point-based techniques operate directly on the points that comprise a point cloud. Recall that points are an unordered list of vectors that contain elements such as position and more meaningful features such as color and normals. These techniques often use a combination of local aggregation, where each point gathers information about the points nearby it, followed by a downsampling step, where the point cloud is reduced in size. Performing these steps iteratively reduces the point cloud into fewer, more meaningful points. State-of-the-art solutions include PointNet, PointNet++, RandLNet, and point transformers. Recent research has been focused on building hierarchical processing structures, speed increases, and attention layers. These are some of the key operations performed by point cloud processing networks. First, the shared MLP, or conv1d, is a fundamental operator. The conv1d is a layer that takes in a single point and all its feature channels and outputs a single output channel. By stacking these conv1d operations side by side, we can create network layers that operate on a set of points with feature dimension A and output a set of points with the same number of points and feature dimension B. This is one of the fundamental operations for point cloud networks, as it allows us to perform channel operations in a permutation invariant fashion, since the layer looks at each point individually, so the order doesn't matter. Second, max and average pooling. Like their 2D counterparts, these operations take a group of points and output the max or average value for each channel over the group of points. This is oftentimes how networks incorporate information from a region into a single point. Third, k nearest neighbors. This is not a learned function, but a necessary component of many of the learned functions. It simply refers to computing the k nearest points to each point. Fourth, furthest point sampling. This is also not a learned function, but is often used to downsample a point cloud. It takes a set of n points and chooses a smaller set m of points, iteratively selecting the point in the original set furthest from the smaller set chosen so far until m points have been chosen, hence the name, furthest point sampling. This operation is used to uniformly generate downsamplings in an unordered point cloud. Finally, self-attention layers are beginning to see use as an alternative way to gather information at a point about its local neighboring points. Once we have processed both the RGB and depth data, we need to fuse them. Point fusion 2018 and dense fusion 2019 first pioneered techniques to fuse data from the color and depth image. They passed the RGB image through a ResNet encoder, followed by a pyramid scene parsing network, or PSPNet, and the depth image through a PointNet point cloud encoder. They then take the encoded features for each point pixel and merge them together with their counterpart with a little bit of additional processing. These techniques were furthered by FFB6D in 2022, which used a bidirectional fusion module to iteratively fuse information from the color and depth images, leading to state-of-the-art results. By combining complementary sources of data, the network can extract more meaningful information. After processing the RGB and depth data, the network needs to perform pixel-wise semantic segmentation to determine which points and image regions belong to an object and will be fed into the object pose predictor. The benefit of performing this task using both RGB and depth data is the problem of scale ambiguity. For instance, the two pliers in this image are the same shape and texture, but have different sizes. Using only RGB data, they are indistinguishable, as a big plier further away from the camera is observed the same as a small plier closer to the camera. Finally, the points and pixels of an object are fed into a pose predictor that serves as the output of the network. Although the end goal is to predict the object's position and rotation in 3D space, directly outputting this leads to less than favorable results. Dense fusion proposed directly regressing a translation and quaternion for rotation, but required a process where the algorithm is iteratively applied to correctly output rotation. The nonlinearity of the rotation space lends to this issue, requiring small rotations to achieve higher accuracy. Some works rely on the continuity of rotation representations in neural networks from 2019 to directly regress rotation, but in a more continuous fashion. A potentially superior output involves guessing the position of key points in 3D space. These key points are pre-selected locations on the virtual model that are evenly distributed throughout the surface of the object. Once the network has guessed the position of these key points, a least squares solver is used to estimate the highest likelihood rotation of the object given the key point relative positions. This technique tends to give better results, but requires a least squares solving step that slows algorithm speed. An even more expensive version of the key point parameterization is a dense UV parameterization, where the network infers for each point in the image where it corresponds to on the virtual model. A least squares solver is then employed again to estimate the object's most likely rotation. As with any deep learning problem, a large burden rests upon the data sets to provide large amounts of high quality labeled data. One of the major obstacles to 3D object tracking is the difficulty of labeling 3D data. While labeling 2D data is intuitive and fast for a human labeler, labeling 3D data requires operating on point clouds and usually involves a combination of human labeling and algorithmic assistance. One of the most ubiquitous datasets is the YCB video dataset, introduced by POSE-CNN in 2017. It consists of 21 common objects ranging from grocery items to tools, and 92 distinct video sequences of a configuration of the objects cluttered together. Each frame of these videos contains a color image and a depth map, and each object is labeled with its ground truth position and rotation, and each image is labeled with a per pixel semantic segmentation. Here are some current results from FFB60, a state-of-the-art solution from 2022. Notice the high quality of the geometric alignment. The color points represent points sampled from the virtual model projected onto the frame using the object's inferred position and rotation from the network. However, the textural alignment is slightly worse for geometrically symmetric objects such as the Campbell's can, as it is a more difficult problem. Another drawback of FFB60 is the runtime, running anywhere from 1 frame per second to 10 frames per second on our computer with dual GTX 1080s. For our current work on OpenARK, we are focusing on improving these results through a combination of hardware and software means, achieving good performance at faster runtimes. Thanks to the students, both Masters of Engineering and undergraduate researchers, who contributed over the last year to OpenARK's digital twin module. Thank you for listening.